So, what if the fastest thing in the universe isn't actually light? Today, we're diving into a fascinating text that really challenges one of the biggest rules in all of physics. It argues that the cosmic speed limit isn't just breakable, it can be totally shattered.
We all learn that nothing with mass can travel faster than light. It's a cornerstone of Einstein's theory of relativity, almost 300,000 kilometers per second. But is that really the final word? The text we're looking at today says, maybe not. And it tries to prove it, not with super complex math, but with a few surprisingly simple thought experiments.
So, how does the author even begin to build this case? Well, first, we're going to look at their core problem with modern physics. Then, we'll walk through three of their main thought experiments, one with a giant rope, another with satellite messages, and a really detailed test involving the Voyager 1 probe. And finally, we'll wrap it all up.
Okay, first things first. To really get what the author is arguing, you have to understand where they're coming from. Their entire case is built on this really fundamental disagreement with how modern physics even sees the world.
I mean, the author comes out swinging with this pretty bold claim. They're basically saying that physics has lost its way, that it's gotten too abstract and disconnected from reality. This is so key because it sets the stage for their whole argument. They want to bring things back to tangible physical examples you can almost touch. And that brings us to their central idea, what they call the rigid material world. In this world, if you have a perfectly solid, rigid object, a push on one end should instantly, and I mean instantly, be felt on the other. But here's the catch. Physics tells us there's no such thing as a perfectly rigid material. A push actually travels through an object like a wave, limited by the speed of sound in that material, which is always way, way slower than light. Just keep that little fact in mind. All right, let's get to that first thought experiment. It takes a really simple idea and just blows it up to a planetary scale to test this whole concept of instant action. So I want you to imagine a rope, but not just any rope. We're talking about a rope that's over 300,000 kilometers long. That's long enough to wrap around the entire Earth 7.5 times. That's the setup. So the author's logic goes like this. If you pull one end of this imaginary, perfectly rigid rope, the other end, 300,000 kilometers away, has to move at the exact same moment. If it did, that tug would have traveled faster than light. But, like we just talked about, that's not how it works in the real world. That tug would travel as a vibration, a wave, through the rope, and it would probably take hours, if not days, to get to the other side. And to make this feel a little less abstract, the author even proposes a real-world test. They say, hey, let's wrap a 297-kilometer string around the big tunnel at CERN, give it a pull, and film it. They claim that even our best super cameras wouldn't be able to spot any time lag. Of course, physics would predict a very clear, very measurable delay. Okay, so from a giant rope, we're now jumping into the world of modern technology for the second example. This one moves away from mechanical pushes and pulls to electromagnetic signals. The setup here is pretty simple. You have two people really far apart on the globe, and they both send a message to each other at the exact same time. And both of those signals have to go way up to a satellite and then back down. And the distances we're talking about are just huge. A typical communication satellite is orbiting at about 36,000 kilometers up. So for each message, that's a round trip of 72,000 kilometers. Now, the author argues that because the Earth is spinning and the satellite is moving, those speeds should add up or subtract from the signal speed. But this is actually a classic misunderstanding of relativity. One of the core ideas of special relativity is that the speed of light in a vacuum is the same for everyone. No matter how fast you're moving or how fast the light source is moving, it's a constant. All right, let's move on to what the author presents as their most detailed proof. This one involves a real object way out there in deep space, NASA's Voyager 1 probe, and this experiment is designed to give a very specific, measurable number. Here's the idea. NASA would send a radio signal out to Voyager 1 and then time how long it takes to get a signal back. They'd do this once, and then they'd wait exactly 6 months and do the exact same test again. Now, this is actually a pretty clever setup because it uses Earth's own motion around the sun. In that first measurement, Earth is moving in its orbit towards where Voyager is. But 6 months later, we're on the complete opposite side of the sun, and now we're moving away from it. The author believes this difference in our planet's velocity should directly impact the signal's travel time. The math the author uses is, well, pretty simple. Earth is zipping around the sun at about 30 kilometers per second. So they just add that speed when we're moving away and subtract it when we're moving towards.
creating this total relative speed difference of 60 kilometers per second between the two tests.
And based on that simple addition, the author predicts a very specific result. The round-trip signal time for the second experiment should be 16 seconds longer than the first. Of course, in the real world, physicists at NASA account for Earth's motion all the time using relativity, and the fact that the speed of light is constant is what makes all those calculations work perfectly.
But for the author, this is the whole point. This is their smoking gun. If anyone ever did this experiment and actually measured a 16-second difference, it would, as they put it, completely annihilate one of the most basic principles of modern physics. Okay, so we've looked at a giant rope, mobile phones, and a deep space probe. Let's just take a step back and pull all these pieces together to see the author's final case. So the whole argument really rests on four main pillars. This idea of an instantaneous tug on a rope, the simultaneous arrival of mobile messages, that predicted 16-second gap in the Voyager signal, and they throw in one last quick point about how light bounced off the moving moon shouldn't return perfectly to its source. When you look at all of these examples together, you can see the pattern, right? Every single one is designed to take physics back to this intuitive material world. The problem is, they do it by ignoring some really fundamental principles that have been tested and proven over and over again, like the fact that signals aren't instantaneous and that the speed of light in a vacuum just doesn't change. And that really brings us to the big question at the heart of all this. The author's arguments feel simple, they feel intuitive, but they go head-to-head with 100 years of real-world experiments that have confirmed relativity time and time again. It just goes to show you that while thought experiments are an incredible tool for pushing the boundaries of science, they eventually have to stack up against actual evidence. And in this case, the evidence we have overwhelmingly points to one thing: there really is a cosmic speed limit.